All right, so let's see. What do we got today? Looking for 7 out of 9. It was 2.36.
That you're supposed to get
Yeah, what'd they get?
3 point something.
Yeah, so that means that it's either wet
Yeah.
or they added their amounts wrong.
It could be wet.
It could be wet. Because if it's wet, it's still holding out.
Because it was so the center can usually be wet. How am I thinking that?
So it needs to be expanded out.
You did not.
All right, this is for the Kaimani. You have been chosen.
This is different.
You see.
This is this side.
I don't have. Where? Huh?
I left it right where I got it from.
No, you did.
You have it right there.
This is my new one from today.
Yeah, that's the one I saw.
No.
You got all 9. All right, give me a round of applause. See, that footwork wasn't too bad. A lot of good results here. Well, Amines did not get a chance yesterday. They had their big exam in organic chemistry, but they will get a chance tomorrow as they start the Chateliers principle. All right, so we are going to go ahead and get started at this time. We're going to go over the bow work, and then we'll get to today's lesson. Make sure that she messages me beforehand because I put you as an amazing Okay, so here we go. Like I said, that after the lesson, you should have a little bit of time to study, go over your mini assessment practice. I put up the answer key to that yesterday, so you could check to see how you did. And then the mini assessment today will be just on lessons 1 through 3. Remember, just like last year, you do need to be present to earn the marks for the mini assessment for your team. So for those people that aren't here, they lost those marks for their team today. But they'll still have other opportunities. There's more competitions to go. All right, so they'll still get the opportunity though to make up it after spring break, but then brain rot happens, so we'll see how it goes. Yes. You can scan through and go. So, generation of the electrophile. This is always one of the points of the mechanism, and most of the generations of the electrophiles are the same. The only one that's different is the nitric acid, sulfuric acid one. I can choose any of them for today. So make sure you study them all if you haven't already in that 15 minutes that you get before the mini assessment. For this one, it would be CH3, CH2Cl, plus you could choose AlCl3, or you could choose FeCl3, whichever one, doesn't matter. And you get this and this for the positive charges wherever you put the CH2. Then they're telling you this is the beginning. So now you would take the electrons from benzene and grab the CH2CH3, which means that in your intermediate you have a benzene ring, but it is broken, right? So you write the little plus there to say that it's broken, that one of the double bonds is missing because you now used it to add on your CH2CH3. And then a lot of you did end up getting this correct intermediate, but then where we lost some marks is understanding what happens next, which is, well, the way that I drew it, FeCl4 minus would come in, grab this hydrogen, and these electrons would fold back in to the ring, and you would get your product. Ring restored. The major mark, just so you're aware, is taking the 2 electrons from the hydrogen and folding them back into the ring. If you don't do that, you definitely don't get one of the marks of the mechanism. So you've got to make sure you do that. Yes.
In the mini assessment, you have to write like the final product and also like.
So you should also have FeCl3, and you should have HCl as your products, because it did say products here. Okay. Yes. Question?
I was gonna ask from the mini assessment, when one of the answers say like different products,
If there's multiple major organic products, you have to include them all. So if 2 and 4 are equivalently being made, you have to put 2 and 4. Because it means they're 50-50. You get 50% of each one. Okay, so this next question is typical reagents conditions. I know when we come back from spring break, you're going to be so happy to do multi-step synthesis with all these different reagent changes you could have. Yes, Chelsea. If then it's just one product. If it's a bulky side chain, like CH3. Okay, describe the reagents and conditions required for step 1. This was knowing that it's CH3Cl. This is a Friedel-Crafts alkylation. And in order to get that CH3 on the ring, you need the catalyst, which is AlCl3 or FeCl3. And I thought it was really weird. This is where the A-level exam sometimes has me confused because this is the answer. This is the answer in the mark scheme. We all know that's the answer. Why did they say describe? Doesn't describe usually mean, like, talk about it? There is no talking about it in the mark scheme. That's literally what the answer is. So, and they gave multiple lines. I'm very confused on that. just saying. I guess if you said, oh, well, the reagent is CH3Cl and the condition is you need the AlCl3 catalyst, that would be describing. But that's not what the mark scheme says. The mark scheme just says CH3Cl, AlCl3. So I don't know. That's the A-level exam sometimes with their directions is really weird to me. But answer how you feel is best fit. The minimum amount you needed to say was that. You got the mark if you said that. Describe, again, the reagents and conditions required for step 2. But again, you did not need to say this in a sentence. You just needed to say it's HNO3, H2SO4, concentrated, and 55 degrees Celsius. They did accept a range. The range they accepted was between 20 and 65 in this mark scheme.
Please pardon the interruption. Teachers, please send down all the students attending the Women of Tomorrow field trip. You received an email yesterday with the names of the students attending. Please send down the students for the Women of Tomorrow field trip. Thank you.
That's what I'm like. Well, it's like our room temperature right now today in this room is about 20. Because it's a cold morning outside, so it gets a little bit colder in the building. But that's weird to me that they accepted that. And typically I see 55. Like it's gotta get better yield product, I'm assuming 55. Yeah. Yes, both. Yes, welcome back. All right, next one. Step 3. This is alkaline KMNO4. That's all you have to say. You did not have to break it up in step 1 and step 2. As long as you said alkaline KMNO4, they accept it as a response. But if you said it was alkaline KMNO4 and then you further acidify it afterwards, that would also be fine. But it's not base and acid at the same time. So the alkaline part is the important part to know that that happens first. And then name compound W, this could have been a little bit confusing knowing what's the ending because there's 2 functional groups. The ending is benzoic acid. So this is benzoic acid. And then you count the nitro group is 4 away. So it's 4 nitro benzoic acid. And that would be the mark there. All right, so that's what we did for the bell work. We're going to go ahead at this time and proceed with the lesson. I copied the slides from last class to start so that we could get those additional practice questions. I didn't want to exclude them. I had stopped a little bit early last class just to make sure we had enough time for the competition. On reflection, we did. We had plenty of time for it, but I wasn't sure. So we're continuing on with the lesson today. We are going to make a hard stop at 8:45. So wherever we're at 8:45, regardless of whether or not we finish, we stop there, and then we continue next class with the finalization of what we're doing. Remember that the lesson 4 and 5 homework is due the Monday we come back from spring break. So 4 and 5 is really just mainly about acyl chlorides. Those homeworks are about phenols and acyl chlorides. We have largely covered that, although we're going to take a look at a little bit more with acyl chlorides at the beginning of class today. The homework on amines and azodies, which is what we're covering today, like the new content of today, that won't be due until later on after spring break. So like the Wednesday, not the Monday after spring break. So I'll put that up after I review the homework to see how much time to give you on that. But the one that's due Monday is 4 and 5. Yes.
So for the quiz that we're gonna take
Today,
right?
1 to 3.
Like
1, 2, 3.
okay, 1 to 3.
It's benzene, reactions of benzene, reactions of phenols. I gave you the mini assessment practice so you could see like what types of questions you could expect. It's from those first 3 lessons, anything that's in those first 3 lessons. The one afterwards, after spring break, which won't be the first day we come back, but like the second day we come back, will include these lessons in it as well. And so it'll be a little bit harder because you'll have more reactions. But you'll have the team competition on Monday. So if you can see today, depending on how far we get, this looks like a whole lot because this is one standard, but it's got 4 parts, and each of these parts is a reaction. And so this right here is 4 reactions, and then we have to describe basicity versus acidity. And then we have more reactions here, and we're going to learn about something called azodies if we get the time. And so we've got a lot to go over today. We'll be going over till I said like 8:45, and then we'll practice review for your mini assessment that I hope you all do well on. All right, so reaction with alcohols and phenol. This is from last class, so this is continued from last class. I technically already went over this, but I wanted to make sure that we did more practice on it, the reactions of acyl chlorides. I wanted you to recognize that acyl chlorides are very similar to carboxylic acids, so the way that they react is very similar to carboxylic acids, meaning if I've got this alcohol group with phenol, but it's still an alcohol group, and I've got this right here, I'm going to be taking out H and Cl to combine the 2 together. So remember with acyl chlorides, you're always taking out the chlorine from the acyl chloride and the hydrogen that's next to the electronegative atom on the other thing that you're reacting it with, the other substance that you're reacting it with. So it's really very much the same as polymerization, where you're taking out a small molecule and you're putting the 2 parts together. And it's just important to know that the small molecule you're taking out is HCl. And when you react isochloride with a phenol, you get an ester on a benzene ring. Uh-oh. We're okay? We made it through yesterday with no breakage. If we make it through today, we may make it to a month. We'll see. But there is a lab when we come back from break on the Wednesday and Thursday for the free classes. So we'll see. Okay, let's continue. So this is practice reactions, and this is a molecule called proline. So you've got some reactions here. First one's with NaOH. They ask you to write an equation for the reaction of proline with NaOH. So what part of proline would react with NaOH? Which functional group? The carboxylic acid. Because this is an acid. You should point that out. And NaOH is a base. And so it's just going to do an acid-base reaction. And so what would Q look like? What would this look like? It would be a carboxylic salt, ONA. And what would the other product be? Water. Okay. Now how do we take that and make that equation? Because they want us to write it like this. So what would we be reacting this with? What's the other reactant? NaOH. And then just recognizing, okay, that's going to become CO2, Na, Una. Everything else remains the same. And the other product is water. And that's it. You get a mark for that. So this is just recognizing that it's an acid-based reaction. On the next slide, they are going to ask us more questions about this. Let me know if we're good to move on. So more about proline. Proline has a secondary amine functional group. Right here. That's a secondary amine. Secondary amines react with acyl chlorides. For example, dimethylamine reacts according to this equation. And they're telling you that the Cl will go with the H here, and you put the rest of it together. And so now they're asking you to suggest, well, what would the structure of R be, the product of reaction 2, given this information? And they've given you more than they need to, like to help you try to figure this out. What would the product of reaction R be? Make this. Can we draw it? So what would be happening? This is proline. What did they tell us reacts with the acyl chloride that they want us to react it with? They want us to react the amine with it, right? So how would we react the amine with the acyl chloride? What would be happening? What's coming out? How do acyl chlorides react? The chlorine comes out, and what of this is coming out? The H that's next to the nitrogen is the one they want us to highlight because that's what they told us that they want us to show, right? Could we have taken the H out of the carboxylic acid? Yes, absolutely, we could have, because that also reacts. But that's not what they're telling you to do. They're telling you to react it with the amine, right? So then take out the HCl, and so what would our product be? We would have this. A lot of this is just making sure we copy paste correctly. And instead of hydrogen, what is the N now connecting to? Where does the N connect to? This carbon specifically, right? The one that's next to the chlorine. So the C double bond O, and then like that. Now they said skeletal, so I'm going to take this carbon out and just make it this. Does that make sense? Because it said skeletal, so I don't need to show my carbons, and I technically shouldn't show my carbon. I should show the other atoms that aren't carbon or connected to carbon. And so that was worth 1 point. It was to write that product. And then finally it says suggest the reagent for reaction 3. So reaction 3 is to go from here to there. Do you remember how to do that? The reagent. That's a carboxylic acid. What is it turning into of? Alcohol. How do you do that? Reducing it. And what is the reducing agent for carboxylic acid? There's only one. LiAl. H4. NADH4 only does aldehydes and aldehydes and ketones, whereas LiALH4 will reduce them all. So if you just need something to reduce, I would actually always choose LiALH4 because you know it's going to work. Whereas NADH4 only works for carbonyl groups. Yes.
So it's not LiEH.
It's not a thing. Not something that they create or use in a lab. Probably just doesn't have the same properties due to electronegativity differences. Benzene can be used as a starting material in the synthesis of cyclohexylmethanol, as outlined below. So this is how a lot of the A-level organic questions look, where they give you some series of reactions with steps, and they ask you to talk about what's happening in each step. As you could tell from the practice questions we've seen, this is how a lot of the organic questions look. So let's see if we can figure out what to do here. It says identify a suitable reagent and a suitable catalyst for step 1. So what would my reagent be to go from benzene to this? The reagent, yes. Fluoroethane, which you can either say by name or you could just say CH3, CH2, Cl. They said identify, so it doesn't matter how you answer as long as you answer the correct substance. Catalyst. What's the catalyst we use for that? ALCL, right? 2 marks. Gift. That's a gift. Those are easy marks. Remember, we have heavy math questions like partition coefficients that are also worth 2 marks. I know where I would go for mine. I would go for these for sure. All right, draw the structure of A. So what's A? A is this thing. What's A? I've looked over so many exams, and it's always like this same thing that they're looking for. What is it? Okay, and what does it become? Yes, but specifically on what?
On the side chain.
No side chain. It's just the side chain is the carboxylic acid. The answer is it's always benzoic acid, right? So that. Like that. The reason why the test is so long is because it's giving you so much space to draw your molecules. All right, so those are the questions that we did not go over last class, but were part of last class's lesson. So if you understood that, that means that you remembered, the material that we've been doing so far. So now we're actually going to start in with our new content for today. We are going to be talking about amines, amides, and maybe azodides today. Here we go. Starting with amines. Before we even talk about amines, do you remember if they're acidic or basic? Are they acidic or basic?
Basic.
Basic. That's why in amino acids, there's an acidic part and a basic part. The acid is the acidic part, and the amine is the basic part. That's how you end up, with that sweeter from what we learned about last unit. Amines are bases by definition. Why are they bases? Because they have the capability to gain H+. So they are bases because they can gain H+, which means that's the Bronsted-Lowry definition. And there's another definition. If any of you are going to be studying for National Science Bowl for next year, there's one other definition of acids and bases that we don't talk about in the Cambridge curriculum, but is totally a theory that's actually super important for organic chemistry. So I've been reflecting on that because it's actually how nucleophiles and electrophiles even work in the first place. They are called Lewis bases. So this is just FYI, meaning Cambridge never uses the term Lewis. But these are called Lewis bases as they are electron pair donators. So actually, in the Lewis definition of an acid and base, it expands the definition of an acid and base even further from what the Bronsted-Lowry definition is. And a Lewis base is anything that has an electron pair that can donate to grab an H+. That's what a Lewis base is. And a Lewis acid is anything that can actually receive an electron pair, like the opposite. So like the opposite. So regardless, amines are by definition bases, not acids. And they always have nitrogen that has 3 bonds and 1 unshared pair, due to the fact that nitrogen has 5 valence electrons. So because of that, 1 unshared pair, that's what makes this have the capability of being a base. This right here would not be a base. Why not? It does not have that electron pair to donate. It's actually positively charged, so it would not interact with an acid in that way. So although your typical amines, primary, secondary, tertiary, are basic. If you did have a quaternary amine, it would not be a base anymore. So I feel like that's fun facts, but important information just about what amines do. How do amines act as bases? Well, according to the bronchoalveolar theory, they act as bases because they accept H+. So they accept H+ from an acid, technically like that. If we think about how nucleophiles and electrophiles act, the unshared pair of electrons is always grabbing the H, right? So this unshared pair would grab the H, and then this would be the conjugate acid, the one that gave the extra H+, and then OH minus would be the conjugate, what? Base. So when placed in water, ammonia acts as a base, which forces water to act as an acid, which means that ammonia is more basic than water, which is what we would define as a base. Something that has a pH greater than 7 on the pH scale, because when when ammonia is placed in water, it's going to release OH minus. And when you have more OH minus in your solution, that gives you a basic solution. So now, what do we need to do for this unit? We actually have to describe and compare the basicity of bases. Just like for acids, we had to say, what's a better acid? Well, now with bases, we have to say, what's a better base? And one of the things you need to remember about acids and bases is they're always the opposite. So whatever makes something a better acid makes it a worse base. And whatever makes something a better base makes it a worse acid, because they're opposing ideas. They're the opposites of each other. So if in acids, what made an acid a good acid? Do you remember? Like, why was a carboxylic acid such a good acid? When we talked about acids, Isa. Withdrawing groups, right? So what makes a good acid is the presence of electron withdrawing groups. So what do you think would make a base a good base? The presence of electron donating groups. So the idea is the more electron donating groups, which I'm going to call them EDGs if that's okay, instead of having to write the whole word every time. The more electron donating groups, greater inductive effect, the better the base. Which means, would a stronger bond between the electronegative atom and the hydrogen be better, or a weaker bond? Because every time we said with the acid that we had an electron withdrawing group, this would weaken the bond, making the H+ leave easier, right? So here, what would we be looking for? A weaker bond or a stronger bond? Stronger bond. So this would strengthen the bond. And in this case, it would be the NH bond, because we're looking at amines. So that's the bond that we're caring about. And so if we compare ethylamine, which is CH3, CH2, Cl, versus ammonia, which is NH3, versus phenylamine, which is this, phenylamine. Does it make sense that ethylamine is the strongest base? And why? Does it make sense that ethylamine out of these three would be the strongest base? So the idea is that in ethylamine, you've got these electron donating groups that are donating electrons towards, this is the NH. Towards the NH bond. So the electron donating groups are donating electrons and strengthening the bond, which makes it a better base, more able to receive additional hydrogens. Yes? Yeah?
I have a CH3,
Where?
like the phenol.
Phenol?
Yeah.
Phenol? You're talking about benzyl.
Oh, it's usually in my spots.
You can look it up. That's phenylamine. Regardless, It is. Because the idea is that with this one, the delocalized electrons are actually pulling electrons away from the NH2. Because remember, the delocalized electrons are an area of it's like they're electronegative because of the extra pi electron. So they pull electrons towards the ring, which pulls the electrons away from the NH bond, which weakens the NH bond, which actually makes it a better acid, not a better base. And so the order would be ethylamine is the strongest, then ammonia, then phenylamine. And I did write the reason here, that the electrons are in the benzene ring for phenylamine. They're pulling towards the benzene ring away from the NH, which weakens that bond, which actually makes it a worse base and a better acid. Phenylamine actually kind of operates like phenol, PHENOL, because it's got that same idea. So it would actually be slightly on the acidic side. You could look up what the actual numbers are, but it would actually be slightly on the acidic side. All right, in the next slide, there's some naming questions. I didn't know where to throw these in, but when you name amines, you basically just name the groups, name sides, ill, end with amine. I think I might add naming amines to AS Chem because it's not hard. So the thing is that the naming strategy is the same as ethers, and ethers don't exist to Cambridge, so that's why I don't really discuss it. But the naming here, you would just count how many carbons you have in the chain. 1, 2, 3, 4, 5. 5 is what prefix? Pent. So we would call it pentyl amine. That's it. Count the carbons, ill, and then add the word amine. Here there's 2 side chains. So what would we say is that? So it's like this: CH2, CH2, CH3, CH2, CH2, CH3, and H. What do you think? How many carbons are on this side? 3. That's prop. So this would be propyl. On this side is another propyl. So how do you think we put that together? Dipropylamine. Yeah, because there's 2 of them. So whenever you have 2 of the same, you call it di. Dipropylamine. Alphabetical. Like if it was ethylmethylamine, or ethylmethylpropylamine, if you had 3. And what about this one? What's C2H5? Another way of saying ethyl, right? That's just this. This is ethyl amine. So to name amines, all you got to do is count how many carbons are on each side, give it the ill ending, and then end it with the word amine. And you've successfully named an amine. On the next slide, predict which is a stronger base, ethylamine or diethylamine, with a quick explanation of why. So is diethylamine stronger or weaker as a base than ethylamine? Just a reminder, ethylamine is this, and diethylamine is this. Which one is predicted to be a stronger base? Go ahead. Diethylamine is the stronger base, so you get a point for identifying which one's stronger, right? Diethylamine is the stronger base. And typically the way that they say this is due to a greater positive inductive effect or due to the presence of more electron donating groups. You can say either of those 2 statements. They say the same thing. So due to, I'm going to say it this way, a greater positive inductive effect. Because I've seen this in the mark schemes this way. And then I'm going to put in parentheses more electron donating groups. And what is the other mark they like us to say when we're talking about acidity or basicity that goes along with this, that correlates with this? Go ahead.
The NH bond is more stable.
So this would strengthen or stabilize the NH bond. It makes the NH bond stronger, which makes the NH bond stronger, which means it's able to receive more electrons instead of giving away its H plus, which makes the NH bond stronger. Lots of comparison questions in here. If you're getting the idea, though, it's really the same type of explanation every time. It's just recognizing whether you have an electron withdrawing group, and if you're talking about acidity, or if you have an electron donating group, and you're talking about basicity. Yes, Andrea. They put positives in the marks, so I would say that. If they actually put, like, if it was an electron withdrawing group, it was called a negative inductive effect, like the opposite. So I would include it. Okay, flashcard time. So there are a bunch of reactions in this lesson that we outlined right at the beginning. And some of them are from AS Chem and some of them are new. So the next set of reactions, I think it's 3, are all different ways we can make amines. So first one, nucleophilic substitution. This one was from AS Chemistry, where if you have a halogen alkane and you add a NH3 to it, you're going to swap out. And you end up with NH2 and HBr. This requires hot conditions, so you put the triangle or the word heat. And the solvent must be ethanol for this reaction. So you do have to remember that for conditions. But this one's from AS Chemistry. It's called a nucleophilic substitution. This is one way you form an amine. The next one is new for this year. I don't believe it's discussed in the AS Chemistry class. And this is the creation and reduction of nitriles. So in a 2-step method, starting with 1 less carbon than the amount that you need, you can take a halogen alkane, react it with CN minus to get the nucleophilic substitution. This gives you CH3CN, but this right here adds 1 carbon. So whenever I want to add 1 carbon to my carbon chain, I want to react with nitrile, and that's always going to add 1 carbon. So if you're doing like, a group competition or a mini assessment, if you see the number of carbons is different in your product than in your reactant by 1, that means that you've used the nitrile at some point because you've added that extra carbon that way. And so step 1 would be to add that extra carbon with the nitrile, but then how do you change that to an amine? Because this right here is a triple bond. And an amine is not that. An amine is this, right? So to get from a nitrile to an amine, you have to add 4 hydrogens. And what's the method for that? There's actually 2 methods that I saw in the text that were described, but the one that's typically used in the mark schemes for Cambridge is LiAlH4. However, you can use either. You can use LiAlH4 or you can use hydrogen and nickel to completely reduce a nitrile down by adding 4 hydrogens into an amine. Yes.
That's too much. Why do we need nickel?
So nickel or platinum operates as a heterogeneous catalyst, so you can get the DARD.
Okay, so
DARD meaning diffusion, adsorption, reaction, desorption, diffusion from when we were covering catalysts.
Does it only happen in the gas phase, or can it also happen?
So it happens on the surface of the catalyst. The reaction, like the reactants meet at the catalyst and turn into products there. So it happens on the surface of the catalyst.
So so for example, if you have
So you need nickel or platinum are the best catalysts to use.
you have a molecule that is too big, or you know, because it can.
It depends, yeah. Yeah, size is a factor. Yes.
So like if we had benzene and we had that as a group.
So yeah, if you did H2 and nickel and you did benzene and you had that in there as well, you would also change benzene to cyclohexane. So if you're not trying to do that and you're trying to keep benzene, great catch, Caesar. You would not want to choose H2 and nickel. You would want to choose the LiAlH4 because that would not reduce the benzene ring. Good catch. All right, continue. This is a flashcard reaction. So that means that these go on flashcards, and it's two steps. One to make the nitrile, and then the second to reduce the nitrile. So this is how you can turn a halogen alkene into an amine. Or just for the second step, how you turn a nitrile into a amine. All right, and then there's this other one that's a very common one that's tested, which is reduction from an amine to an amine. This also uses LiAlH4. The solvent is ether, which somehow now exists. But they still don't ask you to know it as a functional group. I don't know. It does exist. It's very common as an industrial solvent. That's why I continue telling you all about its presence, even though it's not in the standards. This is the reaction. So CH3, CO, NH2. What happens with LiAlH4 is just like with carbonyl groups, this gets knocked down, but instead of an alcohol, when the amine's there, it gets knocked down to an amine. So basically, it's as if the carbonyl group just disappears. Yes.
Dry just mean like in solid state or something?
Dry means no water. And anhydrous or dry means no water. So it's just ether, not water. Which means it actually has a very, very low boiling point and melting point because ethers have a lower melting point and boiling point than water. Most of the time when I've worked in organic or, I've been in organic labs, they'll keep ethers like in really cold freezers.
Would water be a byproduct of the reaction?
Yes, water would be a byproduct.
And second, can you tell me what the properties for ethers are? It's just
Oh, what is it? Usually we use diethyl ether.
no, yeah, but I mean like the physical properties. Because I'm wondering.
It depends. Like I said, it's low boiling point, melting point, and technically, even though it's polar, the longer the carbon chains are, the more nonpolar it gets because it's typically very symmetrical. Maybe that's why they don't talk about them.
It's also that I'm wondering, like in popular media, that ether is usually associated with like prismatic stuff.
Yes,
So I'm
because
wondering
when
why.
you open it, because it has such a low boiling point, melting point, it'll come out. So like if you're thinking about like that misty thing, that's why they choose to use it.
That's interesting.
All right, so now we are going to the part that is interesting of this lesson, meaning we're going to start looking at azo dye creation. What in the world is an azo dye? You might be wearing one depending on the color of your shirt because azo dyes are used often as colorants for clothing. They're used in food coloring. So if you've ever, most people have had food colorings in their food. Some people have had a lot of food coloring. If you make cupcakes, you sometimes add a lot of food coloring to your food. That's usually azo dyes. Some of them, at least, there's some research that says there could be cancerous, some of them. So California has banned a lot of the use of dyes. I forgot what the number of the proposition is. Because of the fact that there's a correlation with some types of cancers. And you may know that in our recent administration, they have last year banned some food dyes from being able to be used. And actually, I think the deadline is either this year or next year, like Doritos and stuff like that. They have to change their ingredients to more natural, like turmeric. And so it's going to actually change the colors of what you see. So if you see the color changes in any of your food or your candies, that means that some of the, food dyes and additives are being changed out to more natural substances instead of those that are created in a lab, much as what we're going to be talking about today is, substances that can be created in a lab. So here we go. First things first, this is a reaction that you have to put on a flashcard. One of those reactions you just gotta know. I'm so excited when we come back from break to give you multi-step organic synthesis pathways, where I give you one thing and then I ask you how would you make this medicine, or how would you make this specific thing, like let's say ibuprofen, and you have to trace the steps on how to get there. That's where we're going with this. Right now we're getting all these little pieces of a puzzle, and then you're gonna have puzzles to put together when we come back from break. So this is another piece of the puzzle. If you've got a nitro group on your benzene, and you want to change that to phenylamine, then you can do that. You're supposed to use tin and concentrated HCl. Put a circle around that. Those are the two that you really need. And then the phenylamine, as it's made, is separated with a distillation apparatus and collected into a separate container. So this would change it from NO2 to NH2. Why would you want to do that? Well, let's say this is an electron withdrawing group, isn't it? So it would direct things that are being added to carbons 3 or 5, right? But what if you needed something not on 3, 5? What if you needed it on 2, 4, or 6? So then you could change NO2 to NH2 via this method. And NH2 is an electron deleting group. So whatever gets added would get added to 2, 4, 6. And phenylamine actually operates very similarly to phenol, like I already said today, which means it's an activator, which makes it more reactive than a regular benzene ring, whereas nitro is an electron withdrawing group. It's a deactivator, so that means that it's less reactive than regular benzene. And so just interesting to know. All right, so this is how we prepare phenylamine. Yes? What? No, not if you don't have the nickel platinum. You don't have the correct conditions. Yes. Go ahead and scan shown up. All right, so give the reagents and conditions needed to make butylamine from butane nitrile. What would we use? We want to change nitrile to amine. I would not use NaBH4. I would use LiAlH4. Which typically you do along with dry ether. Name the bromoalkane that would be used to make the butane nitrile. Let's see if we can think about that. If I want to make butane nitrile, what would be the identity of the halogen alkane that made it? It says name the bromoalkane that could be used to make the butane nitrile. What would it be? What was this swapping out with? Do it in your head. What would it swap out with? Br, right? So it would have been CH3, CH2, CH2Br. What's the name of that? Bromopropane. 1 bromopropane, right? Note the change in carbons. You had 4 because you added the CN. But beforehand, you actually had 3 before the swap out. So you go back to 1 less carbon. When I was studying reactions like this, where we gave you the products and we asked you for the reactants that make it, I remember when my professor said what this was called, because it was like, that's a super cool word. It's called retrosynthesis. So when you start with products and figure out what are the reactants that make those products, that name is called retro, like retro, past, retrosynthesis. The opposite of synthesis, like going backward. I thought it was a super cool term back in the day. I think it's cool. That's why, but yeah, you do retrosynthesis for Cambridge whenever they give you the products and ask you what are the reactants for that. Just sounds really fancy if you tell someone, what are you doing in class? I'm doing retrosynthesis. Like, what is that? You want to impress someone who doesn't know science. All right, name the 2 types of organic compounds that can be reduced by LiAlH4 to form an amines. So what are the 2 functional groups that we can reduce to form an amine with LiAlH4? There's 2 of them. One of them we already saw here, nitrile to amine. What's the other one that we mentioned just a few slides ago? Amide. Amide also goes down to amine by adding hydrogens with LiAlH4. So both of those groups, if I use ALH4, I'm going to end up with an amine as a result. All right. So phenylamine, another reaction for your flashcards. I know you're so excited. Phenylamine acts just like phenol. So that means it doesn't need as harsh conditions as regular benzene. When you react it with bromine, if you have excess, it adds everywhere. No catalyst needed. No catalyst needed. And it adds to 2, 4, and 6. So same idea as what happens with phenol. All right. So now we're finally to how to create an azo dye. Now that we've looked at a bunch of other reactions, a lot of pieces of puzzles, we're now going to look at the creation of an azo dye. This will be the last topic for today. We at least have a few more slides to get through. Hopefully we'll get to the practice questions, and then you should still have time to study. The mini assessment's pretty short, I would say. Yes.
Yes, I don't remember. It's somewhere in electron donating or the
Which one? Amine? Electron donating.
Okay.
It's the same idea as phenol, that it's got those electrons that go into the ring. So reactions of phenylamine. Once you've made a phenylamine, you can make something called an azo dye. But this requires a specific process, and Cambridge does want you, I don't know why, but Cambridge wants you to know how to make an azo dye, which would be, like I said, it gives a lot of clothing their color, like the vibrant neon colors, come from the creation of azo dye. And so what is the formation of azo dye? The first step is you actually have to create nitrous acid. Nitrous acid is HNO2. And in order to create it, your starting ingredients would be sodium nitrate, nitrite, which I do believe we actually have in the lab. Sodium nitrite and HCl. This proceeds via a standard double replacement reaction. Nothing strange here. Double replacement. Where you get HNO2 and an HCl as your products. HNO2 is a weak acid, so it stays together. Because this is a weak acid, it does not completely dissociate, it does stay together. So that's how you create that weak acid. Yes, welcome back. Once you've created that weak acid, you have to use that to help you with the creation of diazonium salt. And so this reaction must be below 10 degrees Celsius. What is 10 degrees Celsius for us? Pretty cold. We're talking about maybe 30, 40 degrees? Like it's pretty cold. 40 degrees.
The
I would say.
32 is
32 is 0, so 40, 50 maybe. Definitely colder than this classroom. This classroom right now is about 20. So this reaction has to be done below 10, which means in practicality, we would use an ice bath. Like this reaction would be run, you'd have an ice bath, like you basically have your reaction mixture like that. And then out here, you would have a bucket of ice, which we call an ice bath. You put it in an ice bath. And that would control your temperature to get it really cold, which is closer to freezing. The thing is that this reaction with NH2 and the HNO2 that you'll make, and notice here it says 0 to 5 degrees Celsius. I pulled this from online, but Cambridge accepts lower than 10 degrees. You make something called benzene diazonium chloride if you do this at the right low temperature, which is N plus triple bond N Cl minus. It's a N triple bond N that's actually connected to a benzene ring, which is crazy. But that's unstable, which means that at a standard temperature, it's going to fall apart. And so at a standard temperature, this would actually fall apart with water to form phenol. And that's actually, if you're trying to make phenol, how you do it. If you have the ability to make phenol, that's how you do it. You start with the phenylaniline, which is phenylamine. You use the Na2HCl, but you keep the temperature above 10 degrees Celsius, and you will make phenol out of this. If it's below 10 degrees Celsius, you make the N triple bond N plus Cl minus thing. Again, really low temperature for this. Once you have this, this is called your diazonium salt. What a name. Diazonium salt. Which you absolutely must have a diazonium salt for a azo dye. So in order to make an azo dye, you first have to have a diazonium salt. And then you'll make an azo dye. Yes. So that's an interesting question. Probably from the delocalized electrons. And it actually matters what size groups you have change the color. So it's interesting that they change the wavelength of the orbits. Because they have all these fancy colors, but you don't have transition metals. So it's interesting you're not using heavy metals and you're getting interesting colors. So the next thing that you're going to do is something called a coupling reaction.
God, that's like the fourth.
Well, I felt like your phone heard the word couple and it was like.
Ew. I know, I keep leaving the ringer on. I know.
Just
Sorry.
saying.
Sorry.
Just saying. I feel like that was on purpose. And it's also recorded. Anyways,
Yeah.
so this is what we call a coupling reaction, where we take two large molecules and we basically combine them together. And this reaction is actually quite fascinating. I don't know the mechanism for it, so don't ask me. Perhaps there is one online. But you actually, right at the 4 position of the phenol group, this actually connects, like these two electrons connect right there. And the hydrogen gets out and the nitrogen goes in. I'm thinking it might be an electrophilic aromatic substitution actually, because this has a positive charge and a hydrogen gets out and that group goes in. So I'm guessing it's probably an electrophilic aromatic substitution. But at the 4 position, why at the 4 position? Because big bulky, right? Big bulky groups are not going to go to position 2. It's going to go across. And it is true in this reaction, it always goes across from the phenol group. And this is an azo dye. This is an example of an azo dye. It always has that N double bond N in the middle. And then you've got 2 benzene rings. One of them has a phenol. This is actually super stable, meaning not reactive once you form it. Because all of this is a delocalized system of pi electrons. Like all those pi electrons are all, and also these 2 donate into the ring as well. So it's like that whole thing is super delocalized and stable. So if you remember from AS chemistry when I did pies like this, it's just like the whole thing is like, the electrons are delocalized around over the whole thing, which makes it super stable. And so if we start with different starting compounds, we actually get different colored dyes. And some of these dyes you may be familiar with, besides the ones that are used to color clothes. I didn't put it here. I thought I put it here. If I didn't, methyl orange. Have you heard of that before? It's an indicator you used in AS chemistry, right? Phenol red. A lot of the indicators that we use in acid-base reactions are azo dyes.
Phenolphthalein?
Phenolphthalein, I have to look at the chemical structure of it. Look it up. It has to have, in order to be classified an azo dye, the N double bond N in the middle. So any indicator that has the N double bond N in the middle is classified as an azo dye. Methyl orange, I remember 10 years ago, no more, 13 years ago, when I was first teaching AS chemistry, I went to a training with a teacher who was teaching it in Doral. And they said that you couldn't purchase methyl orange in certain states. And I was like, why not? And they're like, well, it's banned by a certain proposition. And it's because it's an azo dye. It's not phenolphthalein. We're allowed to purchase it. Yes. Like a closed circuit. It's a closed circuit. So the azo group is when you have the N double bond N in the middle of two benzene rings. If you see that, then you definitely have an azo group involved. Yes. I know, it's about 8:45. Let's do this one question though before we go to start to study. Phenylamine is used to make azo dyes. In the following boxes, draw the structure of the intermediate D and the azo dye E. So just as a reminder, what does NH2 become with these conditions? NaNO2, HCl, super low temperature. What do you get? What's it called? You get this and this. Because they hate you. But benzene will be skeletal no matter what. Structural, they mean the rest of it. If there's a side chain, like CH3, they're writing it structural. So that means in the product, you would keep these as structural and not as lines. That's what it really means. So this is the diazonium salt, right? These conditions make us the diazonium salt. So how would I put this together with phenol to get my product, or this phenol stuff? So here, we get this. Good catch that it's structural. That means I can't write little squigglies there. And where would I write the diazonium salt connecting to which carbon on the phenol? 4. And here they kind of made it easy for you because they didn't even put the 2 positions open, right? But it is always the 4 position because it's big and bulky. So that, and then, wow, that is a terrible looking benzene, but it is 6. All right, so we'll stop there because it is time to get 15 minutes to study and practice for your mini assessment. You have 15 minutes. Yes. This? Where? This is N plus NCl minus. All right, you've got 15 minutes to review and study lessons 1 to 3. I'll put up a timer so you know how much time you have. Organic is hilarious, you said?
This whole last class is lesson 1.
It's 1, 2, 3. Lessons 1, 2, 3. Hilarious good or hilarious bad?
It commits.
It could be good or bad.
Yeah. This is just thing and I don't get it.
CH3COCl.
I actually think it's an electrophilic substitution because it's a positive ion going into a benzene ring, and it has to be at the 4 position. All right, if you can review your flashcards, review your mini assessment, mini assessment starts when the timer's up.
That one and I can't remember times, but I can remember. We will have so much stuff over it. Because I have to focus.
I can't believe Glenn got sick and tired of it and actually attacked me.
Whoa, is that blood?
Yeah, I'm not. The handle is like really old and rickety, and when I picked it up, I have.
Okay, you did get attacked.
Glenn is actually losing his mind, attacking.
That's scary.